Hi, welcome to another edition of Mr. Weis Solves an Old AP Problem. Today we have a really cool problem from 2015, number 5. The setup of this problem is that they give us a function, f of x equals 1 over x squared minus kx. We're told that k is some non-zero constant. And what they're going to do throughout this problem is they're going to have k equal various numbers, and they're going to ask us to do various things throughout the calculus curriculum. Now they're nice to us here. For some reason they decide to give us the derivative. I mean, the reason that they do this is because if we were to make a mistake computing the derivative, it really would make all of the rest of the problem kind of impossible. So they're being kind of nice to us, and that's kind of crazy. They're being kind of nice to us and they're giving it to us, though I really want to say that this derivative is very easy to compute. You should sort of be able to do it in your head using a chain rule. X squared minus kx to the negative 1, bring down the negative 1 to the negative 2 times the derivative of the inside. This is the derivative of the inside multiplied by a negative, so very simple. So, part A, what do they ask us to do? They want us to let k equal 3, and then they want us to find the equation of the tangent line to this graph of f at the point where x equals 4. So they want us to find the equation of the tangent line when x equals 4. Find tangent line when x equals 4. So this is straightforward enough. If you've made it this far in calculus and you're not able to find the equation of a tangent line, we've got bigger problems. So to find the equation of a line, we need two things. We need the point on the line. So let's start with the point. That's the easy part. So that's going to be 4 comma f of 4. So we simply need to plug f into this equation, remembering that k equals 3. So note that f of 4 then is going to be 1 over 4 squared minus 3 times 4. So that's 16 minus 12, which I believe is 1/4. So it is 4 comma 1/4. Next we need the slope. The slope is actually known as f prime of 4. That's the whole point. So we're going to plug 4 into here, remembering again that k equals 3. So we're going to have 3 minus 2 times 4 over the quantity 4 squared minus 3 times 4 squared. So hopefully I don't make any mistakes. But again, in the denominator I think we're going to have 4, but we're going to square it this time, so it's going to be over 16. And then in the numerator we have 3 minus 8, which is negative 5. And then the equation of the tangent line in point slope form is y minus y naught, which is 1/4, equals the slope, negative 5/16 times x minus x naught. And there you have it. This is my final answer. Okay, so here we are back with 2015 number 5. We're on part B. We're dealing with this function, f of x equals 1 over x squared minus kx, where we're told that k is some constant, and in each of the problems we're changing what k is. In part B, we're going to let k equal 4, and the question is, does f have a relative max, min, or neither at x equals 2? So that's the question, and we need to answer and justify our answer. So the first thing we're going to do is we're going to see if x equals 2 is even possibly a relative max or min. This would only be the case if x equals 2 happens to be a critical number for this function. So the question we're going to ask ourselves right now is f prime of 2 equal to 0? Or, don't forget, perhaps it does not exist. That would be enough for us to say that it's a critical number. So let's try to see. We're going to be plugging in f prime of 2 into the derivative, which they nicely told us. So remember, k is 4, so it's going to be 4 minus 2 times 2. I can already see we're getting 0. Over in the denominator, it ends up being 2 squared minus 4 times 2 squared. So it ends up being 0 over, it kind of doesn't matter, even if it's 0 over 0, it's certainly a critical number. But in fact, it's not 0 over 0. I think it is just 4 minus 8, negative 4, so 16. which is 0. So it's what we call a stationary point. The derivative is in fact 0, and therefore the slope of the tangent line is in fact 0, which means that the curve flattens out there. Could be a relative max, could be a relative min. Now, in order to decide this, we have to make some decisions here. We can either use the first or second derivative test to try to answer this question. If we try to use the first derivative test, we're going to have to find any other critical numbers that might exist for this function. That will be important for us. And then we can make a number line and go from there. If we're going to use the second derivative test, we're going to have to take the second derivative of this function. And while I want to say that I think students sleep on the second derivative, it's a very cool thing, actually I think in this case the first derivative is better. So let's start by asking ourselves if there are other critical numbers. And I think we find out that the answer is yes. So the numerator is 4 minus 2x. The numerator of the derivative is 4 minus 2x. That has only x equals 2 as a critical number. But there are some critical numbers of the does not exist flavor, and they happen to be when the denominator equals 0. So yes, when x squared minus 4x equals 0, which happens, I believe, x times x minus 4, which happens at 0 and 4. So now I know what my number line should be. My number line should look something like this. Now, and the reason I need this, I'm actually not going to plug in points everywhere in my number line. I'm only interested in what's going on around 2. The problem is, we don't know what around 2 means. Apparently, being around 2 means with being bigger than 0 but less than 2 on the left side and less than 4 on the right-hand side. But it could have turned out that there was a critical number at 1.9. Could have turned out that there was a critical number at 1.9999. And if we didn't do this and we just tried to think of a number less than 2 and plug it into the derivative to see if it was positive or negative, we could have run into some trouble. So this is f prime of x. I'm now going to plug in stuff. So if I plug into the left of 2, note that the denominator is always positive, so it doesn't actually matter. If I plug in something that's a little bit smaller than 2, let's say 1, remember the numerator here, this is 4, so we're going to have 4 minus 2, which is positive. And then if I plug in something bigger than 2, say 3, I'm going to have 4 minus 6, which is negative. Very important, a number line alone does not suffice to answer this question. We do need to say stuff. So what do we find out is that the derivative is positive, so the function is increasing. Till we get to 2, it flattens out, stationary point. Then the derivative's negative, so it's decreasing. The function is decreasing after that point. So we just found out that x equals 2 is a relative max because f prime of x changes from positive to negative there. And this is known as the first derivative test. Okay, here we are with part C of the 2015 Calc BC exam, question number 5. We're dealing with this function that's defined with a constant in it, and they have, in the first 2 parts, been giving us various values for the constant and asking us questions. This time they're doing something a little bit different. They're saying, of all the functions that look like this for any value of k, are there any values of k that will force this function to have a critical number at x equals negative 5? So we want to try to force f of x to have a critical number, find k, so f of x has a critical number at x equals negative 5. Alright, so that's easy enough. We want to find k, we want f prime of x to equal 0 or does not exist when x equals negative 5. So that seems pretty simple. Why don't we just plug in x equals negative 5 into the derivative and set it equal to 0 and does not exist. So f prime of negative 5, since we don't know what k is, we're going to have k plus 10 minus 2 times negative 5 over 25 plus 5k quantity squared. So let's see. In order for this to equal 0, we would need the numerator to equal 0, but the denominator to not equal 0. So let's start off with that. This seems to happen when k equals -10. Clearly the numerator is 0 then. Note that the denominator is not 0 when k equals -10, because you're going to have 25 minus 50, which squared, which is going to be 25 squared or something, 525 or something. So k equals -10. When k equals -10, f prime of -5 equals 0. How about for the denominator? For the denominator, it looks like when k equals -5, the denominator will equal 0. When k equals -5, f prime of -5 does not exist. Now, let us be clear though, there's actually some issues here. A critical number is not just a place where the derivative equals 0 or does not exist. A critical number is a point in the domain of the function where the first derivative equals 0 or does not exist. So let's see, if we were to have k equal -10, and we go back to the original equation here, so let's look at the original equation when k equals -10. We have f of x equals 1 over x squared plus 10x. Are we allowed to plug in -5 into this? Totally. We can plug in -5 into this and we get something that makes sense. F of -5 makes sense. So we're good. This is definitely one of our answers. K equals -10. On the other hand, let's try -5. If we try -5, we have f of x equals 1 over x squared minus 5x. Are we allowed to plug in -5 into this? Oh, it's plus 5x, sorry, plus 5x. Are we allowed to plug in -5 into this? And I believe the answer is no. F of -5 does not exist. The reason the derivative doesn't exist when k equals -5 at x equals -5 is because the original function doesn't exist. There's no way the derivative can exist when the function doesn't exist. So that means that this is not one of our answers. We're only accepting this one right here, k equals -10. Okay, here we are on the final part, part D of this many multi-parted 2015 AP Calculus BC exam problem number 5. Dealing with this function that's defined, almost completely defined except for this constant k. In part D, we're supposed to let k equal 6 and compute the integral, the indefinite integral of f of x. So that's the plan for part D. For part D, we're letting k equal 6, and we want to compute the indefinite integral of f of x dx. So this should be fairly straightforward. Here we go. It's also probably the hardest part. It's the last part, so let's try to do it. So we're trying to compute the integral of 1 over x squared minus 6x dx. Awesome. So you should recognize, hopefully you don't think that this is the natural log of the absolute value of x squared minus 6x. Very common mistake amongst my students. This is not a natural log. The antiderivative of 1 over something is not the natural log of something. It's very specific. There's no u substitution you can do here either, because the numerator doesn't have like something hanging around to help us out if we let the denominator equal x squared minus 6x. We're squarely in the situation where we have to use partial fraction decomposition. And if I'm being honest, this problem actually gives you the hint that you should use partial fraction decomposition. So let's see how that goes. We know that we're ultimately going to split this up into two integrals. The bottom basically factors. Note that x squared minus 6x factors as x times x minus 6. So we know that this is going to factor as something over x plus something over x minus 6 dx. And each one of these integrals will in fact be a natural log, it will turn out. But we still have to figure out what a and b are. So let's do that work. Let's try to figure out what a and b are. So we're setting up the equation 1 over x squared minus 6x equals something over x plus something over x minus 6. If we look at the right-hand side of this, we find out that we have a times x minus 6 plus b times x over x times x minus 6 has to equal 1 over x times x minus 6. So if we focus our attention solely on the numerator here, we find out basically that 1 has to equal a times x minus 6 plus bx. This needs to be true for every possible x. These two things are supposedly equal as functions. And in fact, it even needs to be true at places where these things don't make sense, namely x equals 0 and x equals 6. So that's what I'm going to do. In class I call this the method of convenient values or something. So I'm going to start off by letting x equal 0 and see what that tells me that a has to equal. If x equals 0, we find this equation becomes 1 equals negative 6a, which implies that a equals negative 1/6. On the other hand, if x equals 6, the a coefficient goes away and we're left with 1 equals 6 times b, which implies that b equals regular 1/6. So given that, I'm actually going to rewrite this very slightly. This ends up becoming the integral, and I'm actually going to split them into two integrals. This ends up becoming the b. I'll write the b1 first since it's positive. So the b1 is 1/6 1 over x minus 6 dx minus 1/6 the integral of 1 over x dx. I just kind of switched the order because the a happened to be negative. Alright, so here we go, straightforward. The antiderivative of this is just the natural log of the absolute value of x. The antiderivative of this is in fact just the natural log of x minus absolute value of x minus 6. Now, you might be confused because I said a second ago that the antiderivative of 1 over something isn't just the natural log of something. But you can do the u substitution if you like here. U will equal x minus 6, and nothing will really change when you make that u substitution. You'll end up just going right back to the natural log. Hopefully you've done this enough that you've started to get used to such things. So this ends up becoming 1/6 the natural log of the absolute value of x minus 6 minus 1/6 the natural log of the absolute value of x plus c. Now there's work we could do here if we felt like simplifying this. Loads and loads of rules of exponents, rules of logarithms can take place if you wanted to do such things, but honestly, just leave it like this. It's a correct answer.